Okay, good afternoon, good evening, good morning, whatever your time zone might be. My name is Louise Huffman, and we're just about ready to get started. I'd like to do one screen check here. Linda and Joe, can you see my slide on your screens?
Yes.
Yes.
Great. Then I think we're going to give it about one more minute so that we're starting right at the time, and we'll get started in just a few seconds here. All right, welcome everybody to the PEI Masterclass series. This is the second in a series. We are happy to have you all here and have people from all over the world and lots of different time zones. So thank you for making the effort to be on the call on this webinar. On the slide, you can see PEI's mission statement. We're a vibrant network promoting polar education and research in the global community. We have a phone ringing on somebody's open mic. Tonight's masterclass title is Natural and Anthropogenic, that pesky word, Climate Impacts, Evidence from Ice Cores. And I'd like to point out two of our sponsors. We have Arcus, who has provided PEI with a secretariat, and we have CLIC, Climate in the Cryosphere, who helps us with the webinar series online and also with our website. So thank you to both of our sponsors. Most of you have visited polareducators.org. This is our polareducator without an S.org. This is our official website. This is also where the discussion group will be. So if you go to the members area, there's a drop-down box where you can join. You have to join first before you can log into the discussion group. But both of those links are found in the members drop-down box. Yikes. Oh, sorry about that. I hit a wrong button here. Our vision statement for PEI, Polar Educators International, is a vital international network of educators and researchers aiming to provide a deeper understanding of current polar science. PEI represents trusted leaders working to inspire appreciation and knowledge of the polar regions, their connectedness to all Earth systems, and importance to all humans across latitudes and cultures. One of the ways PEI is working to meet the goals of our vision statement is to sponsor master classes like this one, focused on the needs of a dual audience, educators and researchers. Just a couple of important reminders. Be sure that you sign up for the discussion group, which will start tomorrow. That's at the polareducator.org website /members. And for tonight and also during the discussion group, if you have any technical problems, you might want to write down this email address. It's polareducators with an S 2@gmail.com. Notice the website does not have an S, but the Gmail does. For tonight, during the presentation, if you have questions for the presenters, there is a question box in your control panel, and you can write questions in at any time. And during the presentations tonight, our two presenters will answer some of those questions. The others will be answered on the discussion during the discussion group online between 30 October and 14 November. And now it's my great pleasure to introduce our speakers tonight. Dr. Joe McConnell is a research professor at the Desert Research Institute in Reno, Nevada. But tonight he's actually presenting from London, England, and we really appreciate him taking the time to be with us tonight. His research interests include snow and global scale hydrology, glaciology, and ice sheet mass balance. He is particularly interested in understanding the role of human activities in global climate and sea level change. His research projects take him to Greenland and to Antarctica. Our other presenter is Ms. Linda Morris. She'll be working with Dr. McConnell today. Linda's the Director of Education and Public Outreach for IDPO, the Ice Drilling Program Office, where she works with scientists to communicate their research to non-technical audiences. She formerly was the Center Director and Director of Education for the Buehler Challenger and Science Center in Paramus, New Jersey, where she led program development, training, and strategic planning efforts serving teachers and students. I'd like to thank both Ms. Morris and Dr. McConnell for sharing their expertise with us tonight in this second PEI's Masterclass series. And now I will share screens with the presenters. This will take just a second. Okay, I am now seeing Linda's screen. So Linda, you can
okay
from here.
I'm just trying to get to my control here to open this up. Doesn't want to let me. Hold on. There we go. Can you see the full slide now, everyone?
Yes.
Okay, super. Thank you so much for the introductions, Louise. Joe, our featured presenter tonight, and I are both with the U.S. Ice Drilling Program, as Louise mentioned, and we are one of the partners that work with PEI on this great outreach effort. IDPO, which is our acronym, works cooperatively with the National Science Foundation to help oversee all of the ice core drilling at both of the poles and to provide strategic direction for development of new drills and technologies. So we work with colleagues across the country, which you can see some of the university sites on the map at the left, who help prioritize future science that can be analyzed by ice cores, and then we make sure that the technology is funded and new drills are developed so that they're ready in time to accomplish that science. I did put an arrow at the left there for where Joe normally hangs his hat in Nevada. And I'm on the other side of the U.S. in New Hampshire here at Dartmouth College. And as Louise mentioned, we're absolutely thrilled that Joe has graciously taken some time from a working visit to London to share his science and insights with us. So we've got a good part of the globe covered just with a few of us here, and hopefully many of the rest of you in Europe as well. Before we begin, I'd like to share a little story about myself that explains why I'm so excited about tonight's talk. And Joe, you are absolutely sworn to secrecy about this. So this job as an outreach director is a new one for me. As Louise mentioned, I started with 10 years in the classroom, and then I ran a space science center. And so outreach was a new evolution of a career that's been very interesting. It takes a bunch of different skills, PR skills, understanding education, social media, and knowledge of science. And when I was hired, I have to share, this is like a mortifying confession, that the piece that I most needed was an understanding of climate science. And some of the public that you scientists may be dealing with, and certainly for some of the students who have yet to be exposed, climate science may not be something that they're strong in. So off I went to my first conference where many of the brilliant ice core scientists were sharing their discoveries with each other, and listened for 3 days in a row to acronym after acronym and term after term that were not familiar to me. So from my last lesson in 3rd grade on weather, I was listening to this high-level science and really missing quite a bit due to some of the jargon that was being used. And so I was really upset with myself, thinking, oh my goodness, they made a mistake. I'm the wrong person for this job. But after reflecting on it, I realized that, you know, really this is the best thing that could have happened, because I really got, from that point on, how important it was that I understand in very clear words what the science was that was being talked about so that I could act to translate that for the public. And I think that it's important because for many of the audiences that you as teachers are serving and you as scientists may be addressing, they're going to be in the shoes I was in as I started to learn this really fascinating science of ice core research. And so I share that with all humility as one of the reasons talking about jargon is an exciting development, and I hope that we'll have fun with it tonight. And I'm not being able to advance my slide here. Hold on. Louise, I may need your assistance on this. For some reason, it's not getting forwarded.
I think we found in the bottom left-hand corner the other day. Yeah, there you go.
Okay, super. Thank you. So Joe's topic for tonight, as Louise shared, is natural and anthropogenic, that pesky word, climate and environmental impacts, evidence in ice cores. This is something that might have been presented this way to many science conferences, but for the purposes of tonight's talk, we'd like to simplify that and just say that we know the world is warming up. We know that human actions are accelerating the natural rates. And we know this because of stuff that we found preserved in the ice. So masterclass series presentations focus on two dimensions. The first is the latest in science discoveries, and Joe in a minute is going to share what he does. And then also how to communicate them more clearly to our audiences. So for scientists, you may be doing demos or public talks to folks that don't have a scientific background. And for educators, to your students, we need to clarify how they can hear this in the best possible way. Louise did mention this is the second of the masterclass series. I do hope everyone has a chance to check out the archived live session at the link that's shown here, and this will be repeated, I guess, once ours is archived. Dr. Richard Alley and Mrs. Nell Herman gave a fabulous presentation on sea level rise. That was the content, and then the communication focus was how to use metaphors to communicate climate science. So please do check that one out. Our tactic for communicating clearly on tonight's broadcast is reducing scientific jargon, and simultaneously we'll be sharing an activity on building students' vocabulary skills. So the goal is to identify and clarify difficult words, not to dumb down the science. I think that's a fear that presenters sometimes have, but to more effectively communicate the concepts to audiences whose background do not include a knowledge of climate science jargon. Later in the online session, you'll have access to this lesson called Invent a Word, which will help your students then begin to build scientific vocabulary skills so that one day they'll be adept at decoding complex vocabulary themselves. So what is jargon? The dictionary provides the most common definition that most of us are familiar with, that the language, especially vocabulary, peculiar to a particular trade, profession, or group is known as jargon, so such as medical jargon. But we'd like to offer some other examples that might be considered jargon as well for the purpose of tonight. So anything, any talk or any written material that you don't understand, and we might need somebody to mute there. We're getting some water flushing sounds and typing. Also language that is characterized by uncommon or pretentious vocabulary and very complex syntax or form, and words that can be vague in meaning. So all of those might be examples of jargon. Within the presentation tonight, please watch for this symbol. So I put this in on a couple of slides to get us thinking and focusing on what words might be considered jargon. Joe and I are going to be bouncing back and forth on this topic, and we'd like to invite you to join in by helping identify terms or phrases that you think are problematic. So not just what I've noted with his head, but anything that you might not understand or think your students might not understand. And type that term or word into the question box as we go along. So later on, we're going to pause and take a look back at some of these and kind of get our heads around what the jargon is, what type it is, and then how we might simplify it. And so with that, I'm happy to turn it over to Joe to do his anthropogenic climate change.
Okay, thanks, Linda, and thanks to Louise and Gary and the others for arranging all this. I take it everybody can hear me okay, is that right? Yeah, okay.
Yes,
I'll
Joe,
assume
you're
so.
coming through loud and clear.
um, so, okay, great. As Linda, I asked because my microphone kept muting and unmuting there on its own. Anyway, as Linda mentioned, I'm in the UK and doing this from a tiny little flat in London. So if I suddenly go quiet, it means that I've lost the internet and Linda will take over. So the messages that I would like you to take home from this presentation are first that in the Arctic, climate is changing before our eyes. And that's also true of the Antarctic, although I'm not really going to talk about that tonight. Ice cores show very clear evidence that industrial and other human activities have affected have influenced the polar regions over many years. And then finally, that changes in the polar regions will impact the rest of the world, including where you live. So next slide, please. All right. The overview of what I'm going to talk about tonight, and I should explain this as I'm trying to thread the needle here between sort of making this appropriate for teachers and making it appropriate also for any scientists who are online. So the first, what we're going to talk about is what is the role of the Arctic in global climate? How is the Arctic climate changing today? And then next we'll talk about, look at the glaciochemical archive, and that's one of those jargon words, glaciochemical archive, and why it is so valuable for understanding climate and environmental change. That is documenting long-term or past climate and environmental change. We'll talk a little bit about how we sample the archive using ice cores. I'll show you some recent results, and then we will just talk a little bit about the future, just a couple of slides about my thoughts about the future. So what do I mean by the glaciochemical archive? I'm going to try to remember to stop and explain when we see the little head with the question mark, explain what that term means. So glaciochemical archive is, kind of break it down, an archive is a place where you store something for a long time. So a library would be an archive for books. And then glaciochemical is exactly what it sounds. It's chemical, chemicals or chemical parameters stored in ice. So glaciochemical archive just means a chemical archive that has been stored in the ice for a long time. Next slide, please. Okay, so let's start with the basics. Where is the Arctic? As I'm sure almost all of you or all of you know, it's the region of the Arctic that's north of the Arctic Circle, so that's about 67 degrees north. Obviously, the Antarctic is south of 60 degrees south. Both of these polar regions are characterized by frozen water in various forms, meaning snow and ice. And this is important because snow and ice are very bright, and that is they reflect a lot of solar energy. So what do we find in the Arctic? As you can see on the slide there, it shows that we see permafrost, and I'll explain what that is in a minute, just in case anybody doesn't know. We also see sea ice, both permanent or multi-year and seasonal or single year. There are glaciers and ice sheets, which together are called land ice, and I'll explain what I mean by that in a second. And then I don't show it on the figure, but much of the Arctic is also covered by seasonal snow for much of the year. And that's important because seasonal snow is also very bright and so highly reflective. So all of that means that the Arctic is bright, and the Antarctic is bright, and it has a high albedo. And albedo is a term that we use in climate science a lot. It's basically reflectivity. So something that has a high albedo is something that's very reflective, like snow, bright snow, fresh snow. Sea ice is much more reflective than open ocean water and so forth. And so let's see. So in terms of what I meant by permafrost, so permafrost is permanently frozen ground. That means it's frozen year round. It doesn't thaw during the summer and then refreeze in the winter. And then Linda had asked me to just point out the difference between sea ice and land ice. So sea ice is generally quite thin, a few meters thick, and it's formed from frozen seawater, not from precipitation. And the big thing is, from a climate perspective, from a sea level perspective, is that it is floating. And so when it melts, it doesn't change global sea level. Land ice is very, very different in that it's, first of all, formed from precipitation, either snow or rain that refreezes. And then also it's removed from the ocean, so it's locked up on land. It's a reservoir that's stored on land. So if you melt land ice, glaciers or ice sheets, and that water flows into the ocean, it will raise sea level. Conversely, if the ice sheets get bigger, you will lower sea level. Okay, next slide, please. So I'm spinning my own version here too. So what does all this mean? Why did I emphasize the brightness so much? Well, first of all, in its most basic sense, the Arctic and the polar regions in general act as Earth's radiator. And what do I mean by that? So if we look at the radiation coming in, striking the Earth, that's represented by the blue line on the graph there on the right-hand side. And that's the incoming shortwave radiation. So that's the net. So that's what comes into the atmosphere and then minus what is bounced back effectively by things that I'll talk about in a minute, but especially bright surfaces. So what do we see? And then the red line, by the way, is the outgoing radiation. So that's thermal or infrared radiation that's going away from the Earth back towards space. So around the equator, the blue line is very high. The net incoming radiation is very high. The surface of the ground is very dark. I mean, there isn't any very much snow or ice in the equatorial regions, and so a lot of that radiation is absorbed. And so together, that a lot of radiation coming in and low albedo, in other words, a very strongly absorbing surface, means that you have a surplus of energy. You have that yellow area represents a surplus. There's a lot more energy coming in around the equator than is going out through thermal energy re-emitted to space. But you can see that's just the opposite in the Arctic and in the Antarctic. In the polar regions, the blue line is below the red line, and that's shown as that deficit. So in effect, the energy has to be transferred or is transferred from that area of surplus near the equator to the polar regions where there's a deficit, and then it's re-emitted to space. And that's what I mean by a radiator. So just as with a car, the radiator is designed to remove or dispel or disperse heat away from the engine where the combustion is happening. The same thing happens with the Earth. There's a surplus of energy, of solar and thermal energy near the equator, and there's a deficit near the poles. So the ocean currents move it to the poles, and it's re-emitted to space. Now you can imagine, just like with the radiator of a car, if it's not functioning properly, say a radiator of a car is clogged with something, then air doesn't pass through it as efficiently, and the radiator stops working as well. And that's sort of analogous to what happens when we change the albedo. When we get rid of some of that ice and snow in the Arctic or the Antarctic, and we turn, say, for instance, sea ice into open water, we're changing the efficiency of the radiator in the high latitudes. And what happens is that the whole system will warm up. The equatorial regions or the mid-latitudes where most of us live will get warmer as the efficiency of the Arctic and Antarctic radiator declines. Okay, next slide, please. So what is the evidence, or is there evidence that the Arctic is changing today? And so what I've shown here is a graph of air temperature over the past 110 years, so 1900 on the left to 2010 on the right. And when I say anomaly, you notice that it says anomaly on the vertical axis. That just means relative. So it's relative to some period. In this case, it's 1980 to 2010. And you can see that during the first half of the 20th century, there wasn't a lot of change in temperature. It's sort of somewhere between minus 1.5 and minus 0.5. But then starting around 1970, we began a very secular or constant change in temperature represented by that red arrow. And so if you look at the left side of the graph, 1900, the relative air temperature was about minus 1.5. And then you look on the right-hand side of the graph, and the relative temperature today is about plus 0.8. So that means the Arctic has warmed over the average over the entire Arctic cap, if you will, from 60 to 90 degrees north, as it says on the graph there. The temperature has increased by about 2.3 degrees Celsius over that time. So it's pretty pronounced, and most of that change has happened in the last roughly 40 to 50 years. All right, so what other evidence? Next slide, please. What other evidence do we have? So if we can look at sea ice, and this is very well, I suspect everybody online has heard of this and seen figures of it, but the sea ice it's very well known that sea ice varies sort of from year to year and within the year from various processes. And so, but it was, as we can see on this graph, which goes from 1865 to about 2010, I guess, maybe 2013, the sea ice extent was fairly constant in the Arctic all the way till about, again, 1970. And then in 1970, it starts a very dramatic drop, very steep and monotonic, if you will. It means only going one direction drop in sea ice extent. So not looking good. And keep in mind that's going to change the albedo, or that is changing the albedo, that reflectivity of the sun, or the surface. It's changing it from being nice bright sea ice, especially snow-covered sea ice, to open water, which absorbs a lot more energy. Okay, next slide, please. So we can also look at ice sheets and glaciers and ice sheets, and I've just shown as an example here the Greenland ice sheet. And so let me explain this slide a little bit. But the bottom line is that the Greenland ice sheet is melting and flowing faster to the ocean. But let me explain this graphic a little bit. This is a 3D image of the Greenland ice sheet, and draped over it is a image of ice sheet elevation change from the year 1993 to 1999. So the way this is done, let me just explain a little bit. The way this is done is that NASA flew a sensor on board an aircraft, and now it's flown on satellite, but at the time on aircraft. And you fly over much of the Greenland ice sheet and make very, very accurate measurements of the elevation. And that's what I mean by altimetry, the elevation of the ice sheet, the altitude of the ice sheet. And then they repeated the same thing in 1999, so 6 years between the two surveys. And what is shown is the 1999 surface minus the 1993 surface. So if it's kind of warm colors, those browns and oranges and yellows and oranges and so forth, that means it's getting thicker at that part of the ice sheet. And the blues means it's getting thinner. So if you kind of, what would you say, defocus your eyes or something, and look at the upper parts of the ice sheet, the higher elevation parts of the ice sheet, you'll see that the colors are not very bright, and they're sort of an equal amount of blues and yellows and grays. And that tells us that the upper part of the ice sheet is pretty much in balance. There's not a lot of change happening in that part of the ice sheet. But if you go down to the edges, you can see you get much darker colors, dark blue, dark purple, almost black. And that's telling us that that part of the ice sheet declined a lot. Between 1999 and 1993, the surface of the ice sheet fell a lot. And what that means is that that part of the ice sheet lost a lot of mass. And so the interpretation of that, or the obvious, what that means is that the edges of the ice sheet are melting away and dropping in altitude quickly, losing mass, and the upper parts of the ice sheet are staying pretty much the same, at least at these timescales. And so that means that the ice sheet effectively is staying about the same height, but it's getting smaller by getting skinnier, if you will. Why do we care? Well, Greenland and Antarctica, there's a lot of, as I mentioned earlier, there's a lot of ice or water locked up on the Greenland and Antarctic ice sheets. And I just show that here. If all of Greenland were to melt and just took that water and poured it into the ocean, it would raise sea level by 23 feet, or about 7 meters around the Earth. Same thing for Antarctica, except that it's more like 200 feet or maybe 60 meters or 65 meters, something like that. So you can see that that would really change things a lot. And you can, if you think about it, think about how much of the world's population lives within, fairly close to the sea level. It would have huge ramifications on our societies, on where we live, on where our industries are located, and so forth. Okay, so next slide, please. Next ice sheet.
Okay, Joe, I'm going to jump in now. Can you hear me?
Yep.
Okay, super. We've had a couple of those little icons, and you've done a great job identifying some of the words, but the purpose of this slide is to bring some focus to the kinds of jargon that we're listening to. So as all of us begin to prepare our talks and our lessons and our presentations, we maybe recognize a couple of these and change some of them out. So glaciochemical and glaciochemical archive, you had mentioned, trapped in the snow, the evidence that comes out in ice core. I listed glaciochemical because of the complexity of the word, and I think of this as a brain stopper. So, you can decode this word, but you have to stop and think about it. What does glacio come from? Yeah, okay, glaciers and chemicals, we kind of know what those are. So if it makes your listener pause and actually think about what the word is, which may interrupt their comprehension. And the word archive, as you mentioned, it's used in different contexts, and the meaning differs a little bit with context. So for me, this is kind of a delayed reaction kind of a word, where I sort of understand what archive is, but my brain pauses and thinks, oh, it's like a library, and then I get the full concept comes through. Permafrost, I think, is a word that might be considered jargon if you were working with younger age students, or younger groups of folks in after-school programs or the public, where they're not using scientific terms. So perhaps at the high school level, permanent frost is pretty obvious in this word, and it might not be such an issue using that with that age level. And I think you mentioned and did a great job describing the differences between sea ice, glaciers, and ice sheets. That was posted because of misconceptions, and many students don't understand the ramifications of melting different types of ice, which you went through, Joe. And for those who are educators on the webinar tonight, I hope you do go back to the last masterclass. I mentioned it previously, but Nell Herman did a great discussion of an activity, number 5C, step by step, that will help your students distinguish the outcomes of melting sea and ice. So that's a resource for you that's on the PEI website. And the last two terms that we dinged, albedo and altimetry, are just examples of pure jargon. They're vocab words you might not know. Albedo is used fairly exclusively, to my knowledge, in science, so you just have to learn it. Altimetry, once again, if you're not talking technical terms and familiar with that, it would be something you'd have to look up. So we're going to keep using different terms as Joe proceeds through the talk, but please do, when you find things that aren't noted, write them into your question box, and our goal ultimately will be to develop a full list of terms that we can watch out for as jargon. So back to you, Joe.
Okay, Linda, thanks. So back to the science. So now I wanted to talk about what drives climate change. And the bottom line is that radiative forcing drives the climate system. That is, the relationship between incoming and outgoing radiation is what drives the climate system. And then changes in the radiative forcing are what drive climate change. And that may be a little bit of an oversimplification, but that's sort of the broad brush way of looking at it. So the climate system is very complicated. So I just want to simplify here, but so basically it's the composition of the atmosphere and the albedo, or that albedo word we used, or reflectivity of the surface together, that determines the radiative forcing. I'll explain that in a second, but remember from the earlier slide that radiative forcing is the difference between incoming shortwave radiation or sunlight and outgoing thermal energy. Remember those blue and, what was it, blue and orange line or something, red line? Anyway, so why is the composition of the atmosphere so important? Well, incoming solar radiation, shown as the little sun up there, those yellow arrows, hits the top of the atmosphere, and then as it starts to pass through the atmosphere, some of the energy, that solar energy, is reflected back into space by clouds and little particles in the air called aerosols, and Linda's going to talk to you about aerosols in a little while. I'm going to talk to you a lot about aerosols. And some is absorbed by gases and those little aerosols. So the rest of the Earth strikes rest of the energy strikes the surface of the Earth, and some of it is reflected, and that's where that albedo or reflectivity comes into play. So even if you have quite a bit of solar energy that makes it through the atmosphere, if it strikes a nice bright surface like fresh snow, most of it, or something like 80 or 90% of it, will be reflected back up. But the rest of the energy that isn't reflected, that makes it to the surface, is absorbed. And when the energy is absorbed, it's converted from shortwave energy into thermal energy or infrared energy, and then it's re-emitted back to space. So this is where the biggest issue happens in terms of climate change, is as it travels back through the atmosphere, some of that thermal energy is absorbed by, again, those aerosols, some by clouds, and then some by greenhouse gases like carbon dioxide and methane. So if it becomes harder, for whatever reason, for the thermal energy to get back to space, then the surface of the Earth warms, and this is basically the so-called greenhouse effect. So when we talk about greenhouse gases, we're talking about gases that absorb thermal energy and won't let make it more difficult for the thermal energy to get back into space. So, as I've said, we would. So that's what I mean by saying that the composition of the atmosphere determines how easily incoming solar radiation and outgoing thermal energy can move through the atmosphere. So, with the reflectivity, the albedo that we talked about, determining how much of the incoming energy is absorbed at the surface. So those two things together, the composition of the atmosphere and the surface reflectivity, are really what cause radiative forcing to change. The solar, and that's because the sun is relatively constant. Okay, so then by measuring, and so what we want to do with ice cores, and where I'm going to go next, is that we would like to use ice cores as a way to reconstruct the history of the composition of the atmosphere. So, and of course the purpose for doing that is that we want to try to estimate what the past radiative forcing was like. Climate scientists would also like to know what caused the composition of the atmosphere to change in the past. So not only do we want to document what it was like and whether it was different than today, but perhaps say something about why it was different in the past. Okay, which presumably helps us predict better how it's going to change in the future. Okay, next slide, please. So how do we do that, or what's the sort of concept behind it? Advance my slide here. So this is just a schematic of what the surface of an ice sheet or a glacier looks like, right? So the snow is represented by those little white circles. So you have falling snow that eventually sits on the ground and forms a surface layer. And then as the snow piles up, and presumably this is a place where more snow piles up than blows away or melts every year, a so-called accumulation zone I'll talk about a little bit more in a minute. And so you build up layer upon layer, and the layer that fell, say, in 1900 gets buried. It was at the surface in 1900, and after 110 years, it's buried, 100 feet or 200 feet down in the ice. And so eventually that snow gets compacted more and more and forms. By the way, once snow is no longer fresh snow, we call it firn. That's a term you might see. Firn just means old snow, and that's highlighted as being a jargon term. But eventually you're going to compress that firn or that old snow to the point where it becomes ice. And that happens at roughly 100 meters. So 100 meters or roughly 330 feet, something like that. And at that point, at some point in time, all of the air pockets that are little voids inside between the snow grains get sealed off. And those form essentially little capsules of air that get captured in that way. They're getting preserved as little discrete samples of air. And they lock in the atmospheric chemistry at the time when that ice, that snow turned into ice, when those little bubbles got sealed off. So if we go to the other side of the graph, the right-hand side, and look at what we can see, kind of starting at the bottom, we can see that we might preserve a layer of volcanic tephra. And tephra is just, some people, it's sometimes referred to as volcanic ash. It's a little confusing because it doesn't have anything to do with burning. It's just little pieces of rock they're ejected by an explosive volcanic eruption. So that's volcanic tephra. So you might have a layer of volcanic tephra that we can measure in the ice. You have chemistry and water isotopes preserved in the ice matrix itself. Then in the gas, we have these little samples of old atmosphere So we might measure things like carbon dioxide, CO2, or methane, CH4, in those little bubbles. And then that red line just shows that at some point in time, if we see a layer that formed somewhere between 1954 and 1963, it'll probably have a lot of radioactive fallout in it, and that's from thermonuclear testing in the 50s and 60s. And then finally, if we get near the surface or throughout the ice, you might find isotopes, water isotopes, or pollutants like lead that we'll talk about, or sea salts or dust. And those four things at the top there are all what I would call aerosols. And I'll explain a little bit more about that in a second. So isotopes, I guess you probably all know what isotopes are, but isotopes are just atoms with different numbers of neutrons in them. It's a little bit complex, but different numbers of neutrons in them, so it makes it heavy. So you can have heavy water, for instance. You can have a hydrogen or deuterium or tritium, which is 1, 2, or 3 neutrons in hydrogen. So I hope I made that clear. But anyway, next slide, please. So the things that I'm going to talk about mostly are the things that I measure in my lab.
There we go.
There we go. The things that I talk about or I study in my lab, the focus of my main focus, I should say, is on natural and on these aerosols. And I just wanted to show this is a little schematic that one of my colleagues, Paul Majewski, put together years ago. But it just shows a little drawing of where these aerosols might come from. So when I talk about aerosols, I'm talking about little particles or little droplets that fly around in the air and absorb energy or reflect energy and things like that. And so that's why they are important for climate. But those things come from phytoplankton in the ocean and lakes and rivers, or bacteria and so forth from lakes and rivers. They come from volcanic eruptions. They also things like desert dust that is blown around in the air is considered an aerosol. We also have things that come out of trees and so forth. And then in the more modern period, we have aerosols that come from anthropogenic or from human activities, industrial activities, and mostly it's fossil fuel burning of various forms or things like smelting and things like that of metals. Let's see, so this little schematic is just one of the things about this little schematic is that it shows that those little aerosols get blown by the wind and go up onto ice sheets, and then they get incorporated into ice sheets. So the snowflakes capture them as snowflakes are falling through the air. They capture them, these little particles, or scavenge is the term we use. They're scavenged from the atmosphere, and they're deposited in the ice sheet and form a record. So let me explain a little bit how that works. Next slide. So this is a schematic of the Greenland ice sheet. A guy named Bernard Stauffer, a big name and one of the grand old men of ice coring science. And it just is very schematic, but let me just, you'll notice on the right-hand side, it talks about I've listed the accumulation zone at the highest elevations, and then the ablation zone at the lower elevations. And the accumulation zone is where more snow falls every year than melts. And the ablation zone is the opposite. It's where more snow melts away than falls as precipitation. And separating these two fundamental zones, the accumulation zone from the ablation zone, is the so-called equilibrium line, and that's where the snow falling equals the snow melting, right? So ice, in order for the ice sheet to not keep getting taller and taller and skinnier, ice has to flow from the accumulation zone to the ablation zone, and that's when we talk about glacier flow. That's fundamentally what's happening, is it's flowing from the areas of accumulation to the areas of ablation. So it's generally from higher elevations to lower elevations. So you can imagine if we want to drill an ice core and get a climate record from it, a historical record from it, what we need to do is go up to the accumulation zone. So we go to the accumulation zone where, as I said, more precipitation falls, more moisture comes down as precipitation than melts away because of sublimation or melting. So you get an annual layer or maybe a monthly layer preserved, and they just keep piling up. And so you can imagine year after year. So you can imagine when we come and drill an ice core through that, we know the surface, the age of the surface, and if we can detect annual cycles in the chemistry, for instance, then we could just start at the top. Say if we collected an ice core this summer, it'd be 2014. And then we can count the annual layers from the surface going down into the ice and date the ice core that way. So we can count back a few years. We can, in some cases, we can count back 20 or 30,000 years. We can count the annual layers back 20 or 30,000 years. And so that's one of the ways that we date an ice core. Okay, so now let me just tell you, there are, next slide please, there are I sort of split ice coring up into sort of three basic scales, if you will. The deepest ones are drilled usually at the tops of the ice sheet, the thickest parts of the ice sheet often, and I would call them that deep and millennial scale, a very long-term scale ice coring. And you'll see millennial scale is identified there. What I mean by millennial is thousands of years scale. So these ice cores would represent anywhere from a few thousand years to up to 800,000 years. The oldest ice core, the longest ice core, or the longest time period represented in ice core to date is 800,000 years long. That's the Dome Sea core from East Antarctica. In my community, in our community, the ice coring world, we're looking, everybody's excited about trying to find million-year-old ice. So we'd like to find a place where we can collect ice that goes back 1,000,000 years. First, just for reference, these kinds of ice cores, these deep drilling projects, usually require lots of logistics. You can see these pictures. There are buildings built on the ice and so forth. They often take 3 or 4 or 5 field seasons to collect an ice core. These ice cores can be 2,000 to 3,000 meters long, or up to 3,400 meters long. So that's 1 to 2 miles long. So they're really quite extensive. They're very expensive to collect, and the ice cores from that kind of project would be brought back and shared by many labs. I think with this ice core program I'm showing, Cycle Dome, I think there were maybe 15 or 20 labs analyzed the ice from that project and for different things. So it's very much a community effort. So next slide. So the next kind of drilling I would say is what I would describe as intermediate drilling. And this would be century scale, or hundreds to maybe thousands of years. These ice cores are typically from about 50 meters long to about 300 or 400 meters long. And just for reference, a 50-meter ice core, or roughly 150-foot ice core, would take maybe a day to 2 days to drill. A couple of people would take a couple of days to drill it. And then maybe a 400-meter core would take, I don't know, 4 or 5 weeks to drill. And it would take a team of maybe 3 or 4 people, 4 or 5 people to drill something like that. And an ice core like that might go back, as I said, hundreds to thousands of years, but those are done by individual groups, or maybe 1 or 2 groups working together. My group has collected quite a few of these kinds of ice cores. These pictures are from one of my group. One time when my group was up collecting ice cores in Greenland. So next slide, please. And then the final type of ice coring that I sort of, the way I look at it, is shallow coring. And this would be decadal to maybe century scale. And these ice cores would typically be 20 to 30 meters long. So roughly, what's that, 60 to 100 feet long, something like that. And they could be drilled in a few hours to a day. Now, I'll tell you a little story, just as a little divergence here, or a little diversion here. When I first started doing this, I was a grad student in the late 1990s. And I was working on a project for NASA where we wanted to collect lots and lots of these shallow cores around the Greenland ice sheet. And the first season, 1997, we were supposed to collect 8 shallow 20 to 30 meter ice cores at 8 different sites around the Greenland ice sheet. And the first 3 went really well. At that time, the way you did it was that you see that ski plane there. That ski plane you'd load up with a bunch of camping gear and ice core boxes and so forth, and you and maybe 1 or 2 people would be flown out, and you'd get dropped off, and the plane would fly back to town on the coast to wait a couple of days before they came back to get you. And so you'd set up camp, you'd spend a lot of time setting up camp, and you'd drill, and then the plane would come back and get you. And as I say, the first, after a couple of days, come back and get you. So as I say, the first 3 sites went really well, and then the 4th site, instead of staying our planned 2 days, we stayed more than a week. We got caught in a storm, and airplane was another part of Greenland, and so forth. And it got a little sketchy. We started we lost our generator because it got filled up with snow, and then our backup stove, our stove broke, and our backup stove broke, and anyway, it was getting pretty hairy, and then they came and got us. But after that, I came up with a new idea, which was called commuter coring. That's how I refer to it, as commuter coring. And in that situation, we sit on the coast and we wait until we check the weather every day, and we wait until the weather clears at the ice coring sites, and then we load up with just emergency camping gear, and we fly out to this, maybe an hour and a half out onto the ice sheet, and stop, and we land and leap out and work really furiously. We don't set up camp or anything. We just work very furiously to drill a 20 or 30, 35 meter ice core, and then throw everything back in the plane and fly off to the next site and do the same thing, and then fly home. And the idea is to be home in time for dinner. And it's a much more pleasant way to work, I can tell you. But anyway, so we did that, and so now this has become fairly standard for these shallow coring efforts, is to do it by commuter coring. And as I say, if you're stuck by weather, you're stuck on the coast where there's a shower and internet nowadays and things like that. So, anyway, so one more, let's see, next slide, please, Linda. So then all of these ice cores, no matter how they're collected, are shipped back to the US or to Europe or wherever, Japan or China or whatever, and analyzed, sent off to different labs. And I'm just showing here that on the right-hand side is a picture from my lab with the two guys wearing the white suits. And hey, Linda, I think you might need to mute. Anyway, so what we can see is, so the idea, just for anybody who has teaches young children, those white suits. Often when school kids come to visit my lab, they assume that those white suits are to protect the people working in there from something that's in the room, and it's of course exactly the opposite. The white suits are to protect the room and the instruments that are in the room from the particles and the contamination that's on the people. So, and that's what allows us to do very, very low-level measurements. So next slide, please. So all of this means that we can get some amazing records from ice cores. And one of the biggest findings from ice coring science over the last roughly 30 years ago was that the idea that climate could change, or evidence that climate could change extremely quickly. So this is just showing the so-called Younger Dryas period, about 12,000 years ago, and this is a record from Greenland. And you can see that how rapidly climate changed. That green line shows the temperature, and you can see that temperature increased or changed by about 20 degrees. First it increased, then it dropped again, and then it increased. And all of that, those increases and those drops happened on the order of in 10 years. You can imagine if we suddenly had a step function or a change in temperature and where we live of 10 degrees, 20 degrees Fahrenheit, or roughly 10 degrees centigrade. You can imagine what that would do to society and everything. So that's one of the major findings from ice cores, is that climate can change very, very rapidly at times. Okay. So
Joe, we're
slide.
going to stop for just a minute and have Louise share if there's been any questions before you get into your specific research.
Great, thanks both of you. There have been a couple of questions. Let me get up here and find it. Joe, I think this one's for you. How was sea ice extent data collected prior to satellite imagery and prior to airplanes in the 1800 data?
Yes, that's a great question. It's mostly reconstructed from ships. So when whaling ships, for instance, were moving around doing their thing, capturing whales, they would record where sea ice was, and a lot of those earlier records were reconstructed from things like ship logs. And then nowadays we use a combination of models and ship's logs to try to reconstruct sea ice. That's a great question.
And then we've actually are gathering a couple of jargon words, so that's good. But we also had a question or a statement from a teacher about the radiative forcing diagram and evidence diagram with isotopes and tephra, and that this might be hard for middle school students to understand that diagram, which, it again, and she also made the point that that might be an age appropriate type of subject matter, but she also had suggested maybe developing some layers, showing different parts going on as layers. So I think that might be, unless Linda, you have something to say about that, but I'm thinking that might be a good discussion question in our discussion forum and gather lots of ideas for some of these slides from teachers all over the world, like how would you present this information and what age students would it be appropriate for and things like that.
Yeah, I think it'd be awesome to share ideas on that. And just to share too, I think the long range picture, and jump in here, Louise, if you'd like, when we're focusing on these communication tactics, sometimes, the graphs might be an egregious or a problematic thing as well, but that might become the focus of a future class where we look solely at what is the visual presentation technique that communicates clearly. So tonight, I think we did have some in there that were over the top for younger students, but we're trying to kind of separate out and think about the vocabulary and jargon aspect, just as we did last time with metaphors, and really appreciate your pointing out the pictorial aspect is also an important part that we can focus on in this series in the future.
Okay, great. Thanks. That was all the questions for right now.
Okay, Linda, you're up. Yeah. So I was going to just say that most of my research focuses on aerosols. And as I said earlier, aerosols are little droplets and particles in the air. And I think Linda wanted to say something here.
Yes, can you hear me? I'm going to jump in here because I want everyone to be honest with themselves and tell me how many of you were thinking this when Joe mentioned aerosols. So we didn't put this in our original list, but certainly words that bring up a completely different image and common use are a type of jargon. And I think the climate communication specialists have pointed out that aerosol is a particularly bad one, where most people in the public, when you mention this is what they think, a spray can. And it also brings up misconceptions that people tie with spray cans about ozone layer destruction and so forth. And so this is another category or type of jargon that we want to be careful of. And Joe, you've got two of the best. Anthropogenic and aerosols are just great.
I'm glad I could do that. Okay, so I'll move through this reasonably quickly, although this is the most important part because this is what we do in my lab. But anyway, so most of my research focuses on aerosols and making measurements of aerosols in ice cores, and we spend a lot of time developing new techniques and things like that for improving our ability to measure these things. So what do I mean by aerosols? As I mentioned earlier, things like desert dust or sea spray, burning from wildfires in agriculture and industry, and that's soot or black carbon, and you'll see that later. And then industrial emissions, things like the toxic heavy metal lead, and then also volcanic emissions. And I just want to show, and the reason this is important is because these aerosols can impact climate, and they can also impact ecosystem health. And all I wanted to do now was really kind of go through and show you some examples of what ice cores tell us about these things. So next slide, please. Okay, so as I mentioned, the ice cores, we go out and collect these ice cores, whether they're deep or intermediate or shallow, and we bring them back and cut. In my particular lab, we focus on what are called continuous analyses. And what we do here, shown in that photograph there on the upper right, is a longitudinal sample of ice. Now, what do I mean by longitudinal? So an ice core typically is cut into roughly 1 meter long pieces, so 3-foot pieces, and we ship it back to the lab or back to the US or back to Europe or whatever in these roughly 1 meter pieces. And so then when we get them back there, we cut them. If you can see the cylinder of an ice core, it's a fern core on the lower left-hand side. And you can see that cylinder, it's about, if you put those pieces together, they'd be about 1 meter long. And they are about 10 centimeters or 4 inches in diameter. And so we take those and we cut these big longitudinal samples from them. And so they're about 1.5 inches by 1.5 inches or 3.5 centimeters by 3.5 centimeters on a side, and about 1 meter long, or about 3 feet long. And so you can imagine a big long stick of ice, and we load that up into a melter that we developed, and we slowly melt it, and then we suck the water off and analyze it in real time. And that's what you can see. Those tubes are for sucking the water off and sending it off to those analytical instruments. Next slide, please. So this is where I want to just show you a few examples. So let's start with desert dust. Just so you don't think I'm crazy, you can see this is a satellite image from NASA. And you can see it's a little hard for me without the pointer to show you, but you can see this is southern Patagonia, the east coast of Patagonia, so that's the South Atlantic off there to the right. And right about where the pointer is right now, you can see those things that look like white clouds, but if you trace them back, they go to a very specific point, just a little ways inland. Yep, those are depressions, dried lake beds basically, and the wind is coming, and Patagonia is famous or infamous for its wind. And the wind is coming down over the Andes and sweeping across Patagonia, picking up that dust and blowing it out into the over the South Atlantic. And some of that dust makes it, or quite a bit of that dust in fact, makes it all the way to Antarctica. And so let's look at an ice core. You can see down there that image of on the lower left, you can see an image of Antarctica, and we're going to look at an ice core from that red triangle. Next slide. And so this is what it looks like. This is what the record looked like. And so this record goes back, you can see on the horizontal axis, goes back about 170 years, more or less. This ice core was collected by colleagues in Argentina. And then we were able to get some of it, bring it to Reno, and analyze it in my lab. And I'm just showing aluminum. So that's a record of aluminum. That the upper two figures look a lot alike, but they aren't identical, but they do look a lot alike. And they're showing changes in dust deposition and dust concentration over the last 170 years. And what stands out is that they're mostly blue to the left, the older time periods, and mostly red to the right. And then if you look down at the next level, there's a southern hemisphere air temperature record, and that's based on tree rings, has nothing to do with our record. And you can see that the record of temperature looks a whole lot like the record of dust from Antarctica, from the Antarctic Peninsula. And so what is that telling us? It's telling us that dust concentrations and dust deposition was much lower 150 years ago than it is today, and that there's been a pretty significant increase paralleling temperature change that started about 100 years ago, so about 1900. So this was the first ice core evidence of a major change during the human industrial period in Antarctica. So it was quite exciting at the time, about 6 or 7 years ago. Next slide. So we'd like to know what caused, or we'd like to speculate about what might have caused that change over time in dust. And it turns out that if you look at what happened in Patagonia, sheep were introduced by Europeans in the right around 1900. And southern Patagonia became a major sheep grazing area, and people overgrazed, and that damaged the vegetation, relatively fragile vegetation of Patagonia, and has resulted in this big increase in desertification. So what do I mean by desertification? I mean taking land that wasn't desert and making it become desert. And so that's a term you'll see a lot in climate science, is desertification. At the time, we were trying to figure out how much of it was caused by land use, that is grazing sheep, and how much of it was caused by temperature, because remember how much the change in dust looked like the change in temperature. And the problem is we can't separate the two because they happened exactly at the same time. So it's really where you need models or additional data to try to understand what caused it. But the bottom line is that a combination of land use and climate warming has resulted in quite an increase in dustiness in this part of Antarctica. Okay, next one. All right, so an area that I've spent lots of time working on for the last 6 or 7 years has been burning aerosols. And when I say burning aerosols, in my lab, we developed a method for measuring black carbon in ice core. So black carbon is basically soot, just like you'd see in any fire or whatever, in your house or whatever. And these emissions of soot can come from forest fires, as I've shown on the lower left, or from fossil fuel combustion. And black carbon, or soot, because it's so dark, has a very, very big impact on climate. Next slide. So this is just shown schematically in the next slide. This was a slide put together by NSF for a paper we had that came out on this. And so you can see schematically forest fires that create these little black balls or brown balls of soot. And then you have industry doing the same thing. And those emissions get transported from Canada and the US up to Greenland where they're deposited, and that's where we drill an ice core and measure them. And that's important because that soot ends up especially in snow, and even the tiniest amount of soot can really dramatically decrease the albedo, the reflectivity of snow, and make it melt out faster, and there are all kinds of climate impacts associated with it. So next slide. So let's see what the ice core record tells us has happened in the past. And the other thing about the ice cores is they very much help us put the modern measurements, meaning since we've had satellites for the last 30 or 40 years, maybe even 10 years for some satellites, it puts those modern measurements in perspective, in historical perspective. So what do we see? Well, remember, we measure lots and lots of things in an ice core, not just soot or black carbon. So on the right-hand axis, I've plotted vanillic acid, and don't worry about what it is. Just note that it comes from forest fires, mainly conifer forest fires. And the boreal forest, the northern forest, is mostly made up of conifer, or largely made up of conifer. And so you can see that before. So this record represents back to 1788. So you can see on the horizontal axis it goes from 1788 to about 2010, and you can see that up until about 1860 or so, the blue line, the blue dotted line, and the black line look a lot like each other, right? So that's telling us that most of the black carbon at that time was coming from forest fires, probably boreal or northern forest fires. And then around the end of the 19th century, so around 1860 or 1870 or so, the blue line and the black line diverged from each other, and then they join up again in the 1950s. In the 1950s, they're more or less the same, the blue and the black, but not exactly. So anyway, what this tells us is that where those red arrows are, it means that is not coming from biomass burning. So most of the record is coming from biomass burning, but for that 100-year period from about 1850 or 1860 to 1950, there was another source of black carbon. It was quite a large source of black carbon. So again, we measure other things. So next slide. So here we're going to use sulfur from industrial emissions. And you can see that's non-sea salt sulfur, just think of it as sulfur, plotted on the right-hand scale in red. And you can see that earlier on there we had those big spikes. You can see the big spikes to the left in red. Those are volcanic, the sulfur from volcanic eruptions. So they're very short-lived. They're just big spikes, and then they go away. And that's what most volcanoes look like. But you can see that starting around 1850, 1860, right around when that black carbon starts to rise and diverge from the earlier line, that's when you see sulfur takes off. And so that's telling us that the black carbon is clearly coming, that increase in black carbon is clearly coming from industrial emissions. And just sort of, I'm not going to show it, but reading between the lines, what that means is that's mostly coal burning. When we were, particularly in North America, we're burning coal very inefficiently, and we're producing a lot of black carbon. And then in the 1950s, a couple of things happened. One is we started burning coal much more efficiently. We used scrubbers and raised the temperature and things like that, so that reduced the black carbon. And then secondly, we started switching to oil and gas, which produces a lot less black carbon, but still produces sulfur. So you can see that's why the sulfur goes back up, but the black carbon drops. So that's an example of biomass burning or burning aerosols. Next slide, please. And so then we can look at industrial pollution. So here I'm going to expand the scale. We're going to look at an ice core from, you can see on the map up there, from northwest Greenland. And this record goes back about 900 years, something like 900 years. So from about 1150 to about 2000. And so I'm plotting lead. You know, lead is a bad actor. Lead is toxic heavy metal, and what I mean by that is it has no role in metabolism, so it's only bad. And in terms of modern world, exposure to lead can reduce the IQ, so it's not a good thing to have around. Anyway, if we look at the history of lead, so this record shows the history of lead over the last 1,000 years, lead deposition in northwest Greenland for the last 1,000 years, roughly. And just for perspective, I put in there's Genghis Khan dying in the around 1200. And then there's Columbus crossing the ocean blue in 1492. And you can see that lead has started to come up a little bit even back then, as early as 1500. And then we have the Declaration of Independence in whatever it was, 1776 or whatever. And you can see lead is really starting to come up there. That's also the so-called first industrial revolution. And then in the second industrial revolution, the one we all think of, in the late 1800s, that is a big jump in lead at that time. There's a dip in lead pollution for the Great Depression when everything the economy kind of shut down. And then leaded gasoline is invented, and we have a big time industrialization. We have a rapid rise in lead all the way till 1972. And that's when the Clean Air Act in the US and similar legislation in other countries is passed. And we see this big drop in lead contamination or lead pollution that starts in 1972 and drops way back down, not down to zero, not down to pre-industrial levels, but drops a lot, right? Something like 90% or 80 to 90%. So this is the Greenland. Now let's look at Antarctica. Antarctica, this is work that was just published a couple months ago. We collected a bunch of ice cores from around the Antarctic, I think 15 ice cores all around Antarctica, analyzed them and stacked them all together, and this is what we get. So this is a record over the past 410 years of lead deposition in Antarctica, sort of continent-wide, if you will. And you can see big changes. So really, really surprising results. You can see that the switch from red to blue is almost like, or blue to red, I should say, is almost like turning on a light switch. You go from very low levels to much, much higher levels, very obvious pollution of most of the Antarctic continent. And it turns out that this, you can see that down the lower left panel is a smelter in Australia, a lead smelter in Australia. And most of this lead can be traced back to having come from that source. So it's kind of mind-boggling to think that a single source could have contaminated so much of Antarctica, much of the Antarctic continent, and also a large portion of the southern hemisphere. The other thing that's really surprising is that this lead pollution arrived at South Pole 22 years before polar explorers. And that's Amundsen shown in there in December 1911, arriving at the South Pole. And the idea that if you would have told people at the time that anthropogenic pollution or human industrial pollution had arrived at South Pole 22 years before they did, no one would have believed it. It just shows you how even the most remote parts of Earth are experiencing contamination. So next slide is to show some work on sulfur aerosols. Keep in mind there are two sources. There's volcanic eruptions, and it's a beautiful shot of a volcano punching through the up into the stratosphere in Alaska, or sorry, in Kamchatka in Russia, and then also from industrial emissions. So if we look at that record, same kind of thing as that lead record. Next slide. Over the past roughly 900 years, you can see, again, same ice core. You can see that there were records pretty low until the early 1900s when the industrialization takes off. But you have these big spikes, and those big spikes are from volcanic eruptions, as I mentioned. Just identified a few on there very clearly. That one in 1816, the Tamboran eruption, is the one that resulted in a year without a summer in much of the northern hemisphere. We can also do this in the southern hemisphere. Next slide, please. We can also do this in the southern hemisphere, and you can see that we've stacked a whole bunch of ice cores from all over Antarctica. This is some work one of my postdocs did, and to come up with a record of radiative forcing, or forcing from volcanic eruptions over the past 2,000 years. So, and then now let me just switch gears to finish up and talk a little bit. Next slide, please. Talk a little bit about the future. So this is that same slide of lead that I showed a minute ago. And you can see, the reason for showing it again is to show that while lead contamination has dropped a lot over the past, say, 10 years in Antarctica, and that's a result of doing things like getting rid of leaded gasoline in Brazil or in Australia or and so forth, New Zealand and so forth, the major economies in the Southern Hemisphere. You can see that levels, while they've dropped a lot, they're still way above where they were before the Port Pirie smelter turned on in the Industrial Revolution. So the point here is just that we are making progress, and what we're doing is good, but we still have a ways to go. The other thing I wanted to say is that different industrial activities lead to different forms of pollution, aerosols, and these have important differences on climate and the environment. So the other thing to keep in mind in all this, the other take-home message, is that aerosols are short-lived. That is, they stay in the atmosphere only for a very short time, so sort of days to a couple of weeks, maybe a few weeks. Next slide, please. So the forcing that we get from aerosols, we can stop tomorrow. We just have to stop emitting those aerosols. Now, we could do that for some of our pollutants from smokestacks and so forth, but we can't really stop forest fires, and we don't want to really stop forest fires. So some of the aerosol we just have to accept as being part of the natural system. But this is very different than greenhouse gases. So greenhouse gases, something like carbon dioxide, lasts in the air, has a lifetime of something like 50 to 100 years. So CO2 or carbon dioxide that we release today is going to be in the atmosphere for another 50 to 100 years. It's clearly going to be handed down to our children or to our grandchildren. And so that's why, ultimately carbon dioxide is what's going to change the climate. Aerosols are important, but they're relatively short term, and we should keep that in perspective. The big picture is we have to reduce CO2. And then the other thing I just wanted to say was, as I say on the top there, the longer we wait for the inevitable switch to renewable fuels, the greater will be the climate impact. There's no question about it. And the most surprising thing is that we know we'll have to switch. It's just a question of how much we're going to change the climate of the Earth before we make that switch that we have to make anyway. So I think, one more slide. So one more slide. So I like to finish. So let's see what we've learned. And I'm not exactly sure how we're going to do this on this, but just here's your little quiz for you teachers out there. Get to turn the tables here. So we have four different arrows. There's a blue arrow, a yellow arrow, a green arrow, and a purple arrow or a magenta arrow. And the question is, which do these things represent? So what we see is Greenland sulfur in black and Greenland lead in red over the last 250 years from an ice core. So basically your choices are down there at the bottom, A, B, C, or D. So I think, go ahead, Linda.
Joe, we need to run through this very quickly, but so the task would be to match up the blue arrow with A, B, C, or D, and just type, 1A or 1C, whatever you think it is, quickly into your box. And let's give you just a minute or two to do that. And then, Joe, if you can describe what the answers are, we'd be ready to take more general questions.
Okay, how about let's go to the conclusion. Well, no, we're not. Okay. Whenever you're ready to, just let me know when you want me to give the answers.
This is Louise. How about if we take this slide and put it on the website and let people discuss it, and then maybe during the next 2 weeks we can give the answers to these. I want us to be sure we have plenty of time for Linda to talk about her activity, and then we're collecting questions. We've got some really good questions, so if there's a few minutes at the end we can pose them. Otherwise, Joe, maybe what we can do is send them and have them on the website. How does that sound?
Sure.
Sounds perfect.
Okay, so last slide then. I'll just finish the conclusions there, but just basically the take-home messages that we talked about at the beginning. Polar regions are critical components of the global climate system. That is, they're the Earth's radiator. Their Arctic environment is changing rapidly. We can document that in ice cores, and we can show that humans have had a significant impact for the past 150 years. And finally, the future of the polar regions depends on us. So thank you very much.
So Joe, thank you. Louise, would you like to answer a few of the questions now?
Sure, I can pose a couple of them. We're collecting them. We've got some really good ones.
Or we can just post them, whatever your preference is.
There's really some good ones. Why don't we post them and maybe you and Joe can answer those during the discussion. How about that?
Okay, we are running short on time. It's 5:20. It's my hope to spend a quick amount of time here running through a really neat educational activity that's hands-on. I certainly understand if folks would need to move on, but I will continue working through the rest of this and take questions both for Joe and for any of the educational things at the end. So hopefully if you don't have a chance to stick with this, you can catch it in the archive afterwards. But what we're going to do is walk through first an activity called Polar Detectives, and I referenced information about a second activity, Inventor Word, which I will not take time to go through now, but it's a word formation activity that will be available online. The Polar Detectives activity will be listed in two versions. One is shorter. It doesn't involve graphing, and so it's something that would be appropriate for scientists who are online that would like to have a quick demo to use with a public group to do the modeling aspect of the shorter activity, and then there's a longer version with the full graphing for schools. And as well, once you get into your discussion groups, there will be an article for all of us, both scientists and educators, on communicating the science of climate change, and there's some expert resources there. So Polar Detectives, I wanted to thank Joe as well. He was instrumental in the development of this activity, and it features the use of his ice core data. So Joe, thank you so much for that. The key idea here is that evidence is preserved in ice cores and can provide information on past climate changes and hopefully help produce accurate models for what may happen in the future. For teachers who are in the U.S., I think this helps to address the next generation high school standard ESS 3B, which talks about natural hazards and other geological events and how they've shaped the course of human history at local, regional, and global scales. And so what you're looking at here is just the activity packet cover. It's geared towards students in the middle or high school grades, although upper elementary or grades 5, 6, ages 10, 11, 12 probably can do the modeling aspect as well, but it can be used as a demo as well. And links to both are on the website. As you can see, the materials are minimal and they're for the most part inexpensive and readily available. So you're looking at little prepackaged bits of sugar and salt and pepper. If you have hand lenses, those are very helpful to use as well. Little pieces of black paper, and I have used a very inexpensive plastic cylinder to model the shape of the ice core. So that's basically all you need to run this activity. This is the way I would typically set this up, like at a conference with other teachers. In the classroom, or you might want to use larger boxes of sugar and salt and have student teams divvy up the materials rather than using up all this plastic bags. So the activity begins with a discrepant event that we hope grabs student attention from the start. So imagine what your kids would say if you told them that summer was going to be canceled. And in 1816, which was nicknamed the year without a summer, Joe just referenced that, severe weather conditions did cause Europe and North America to experience a very, very cold season with temperatures so low that crops failed, and there were many environmental impacts from it. So the activity poses a question, what might have caused the year without a summer? And one hypothesis would be maybe we could look back in the record to 1816 in ice cores and figure out what impacted that unusual weather event. So it starts by having taking a look at what we already know about snow. And so scientists are familiar with the fact that snow changes and forms different sizes and types of crystals depending on the environmental conditions under which it is formed. So fine crystals form smaller size crystals in dry, cold temperatures, such as East Antarctica. And fluffier, moister snow, I think of it as like snowman snow when there's more moisture and humidity in the air. And so the activity uses sugar, which is your upper image here, enlarged as a simulant for summer, the fluffier snow, and salt, crystals for a simulant for the winter snow. And in the picture, you can see teachers working through the activity and the role of their students by examining and trying to observe and share different physical properties of this simulated snow. So you could have a class discussion about things such as the size of the crystals, the shapes of the crystals, their colors, which actually are different, the aroma, if there is one, or even taste. And so students begin to analyze the physical properties. And these are just some scanning electron microscope pictures of different forms of snowflakes, and I think it's fun to see these. Some students may feel that all the snowflakes are the same sort of Christmas-related shape that we usually see in holiday images, but you can see there's a very diverse range. Some of these are broken, but fine needle-like flakes, and then plated flakes, and various other versions. So they can relate that to changes in crystal appearance. And so, as Joe showed you in the building of the glaciochemical archive, the snow builds up in layers over time. And so once the kids notice differences in snow crystals, they can then look at these images both in the ice core that they're building, but also in this snow pit picture of the different ways that the summer snow and the winter snow appear as they build up in layers and eventually get transformed into an ice core. And so Joe mentioned being able to count backwards through the archive. As you dig a deeper core, people can actually count out annual layers to see where they are in history compared to when the snow was laid down. And so the next picture is just an image of what results as your students build the snow core, the ice core, out of their simulated snowflakes. And the lesson plan calls for them erupting periodically, which is always very fun. They take the pepper as a simulant for sulfur and ash and can add that in layers. And so this is one very restrained group that came up with a pretty clean ice core on the left. And this is an image that's a fabulous one taken at the West Antarctic Ice Sheet Divide, or Waste Divide, by Heidi Roop. And here you can see this very, very prominent ring of ash that was detected in that core. So fun to have them see the real effect. So then for older students, the question becomes, well, we know what we can see and what we can find out from the physical properties of ice cores. What cannot we see with our eyes that might give evidence of what happened in 1816? And so that was a question that scientists posed and actually designed two separate investigations in Greenland and in Antarctica to retrieve ice cores and do analysis of the unseen factors in the ice. So here I've stuck in this image of atmospheric circulation, so to make sure that comprehension of the data that they're going to be working with is known before you start, you may want to have discussion about where stuff goes when it gets up into the atmosphere. And so higher latitude volcanic eruptions, such as what happened in up in Iceland, might go up into the atmosphere and get blown over onto Greenland, but not get deposited down here in Antarctica because of the airflow patterns. And that's, in fact, I think, Joe, what happened to you when you couldn't get to Greenland one summer when Isle Waffle, I can never say that correctly, erupted. Whereas volcanoes that occur somewhere in the mid-equatorial region tend to get carried in both directions and deposited in both ice sheets. And so that's an understanding that the students need to have before they take a look at the data. And here you can see the data charts that are included in the activity. This is Joe's sulfur analysis. The concentration, the volume of the eruption also can affect the concentration in the ice as well. And so for the latter half of the activity, you have students actually graphing out the Greenland data versus the Antarctic data and coming up with their image of sulfur in parts per billion during the time period taken from the ice cores from 1780 through 1820, which encompasses the year without a summer. And Joe, I'll let you jump in here and quickly tell us what we're looking at.
Okay, thanks, Linda. It's just the blue line is the Greenland data, and the magenta line is the Antarctic data. And what you can see is that the two eruptions on 1810 and 1816 were seen in both Greenland and Antarctic ice. But there's that big record, that big giant thing in eruption only in the Greenland record in 1783, And the point there is that the Greenland eruption, the big bump in 1783, is the Laki eruption in Iceland, and so it's quite close to Greenland, so it dumped a lot of sulfur. Even though it wasn't really that big an eruption on a global scale, it was a very big eruption in the North Atlantic. And so that's why you see it there, but there's absolutely no hint of it at all in Antarctica. And so we can use this to identify, we can use whether it's in the north, in the south, or in both, as an identifier of where the volcano was that when it erupted, where the volcano that erupted was located.
Okay, so we've got overlapping north and south eruptions during the time period when 1816 occurred. So evidence in the ice that sulfur was found during that period from a volcanic eruption. So there's some critical thinking that you can, and discussions you can lead your students on. One thing I did not put in here, and I meant to, but it is included in the lesson plan, is a way to assess their knowledge and whether they're transferring this understanding to other situations. So there are some preset post questions that you can use to evaluate student learning if you should so choose. And then just quickly, this is the U.S. Ice Drilling Program website, and it contains general information, the science projects, the drill technologies, all kinds of announcements and newsletters. I did circle here the education tab off of that, which brings you to the Climate Expeditions website, which is more education focused and outreach focused. You can also get there directly by that link, and each of these pages, I hope, contains additional resources beyond this lesson plan that you will take a look at and enjoy. So on the teachers page, we have activities, also nicknamed Learning Expeditions. There are lesson plans there designed by IDPO, the Ice Drilling Program Office, as well as links to multiple other quality activities on this theme, an opportunity for video conferences with your classroom. There are resources for you. I did want to point out there is a PowerPoint presentation including some basic slides and images that you might enjoy using in your instructions, so do take a look at that. And then under professional development, there are several web seminars from other leading researchers that have been presented in archive that you could take a look at to help build some of your own background knowledge on related topics. The student pages, there's some activities that tie up with a teacher page activity called Checking Out Your Team. But I wanted to make sure for everyone to point out the ice science hotspots, because one of our goals is, of course, to inspire younger students to get literate about science, to get excited about science and engineering, and to hopefully pursue a career path or at least become knowledgeable consumers of helping the climate in the future. So I showed the map initially. These are all pop-ups with contact names at U.S. universities with powerhouses and ice cores, so kids can look up who's doing what kinds of things they're researching, go to their web pages, and know who to call if they have questions about getting into programs like that. As well, we have sort of career profiles, personal stories about how people got into this field. They're not all scientists, some are support people. And then on our very first page of our website, in a section called In the News, are some research page summaries, including the personal stories of some of our leading researchers. So hopefully that's inspiring to your students who would like to know who's doing what and how they got into it. And Joe, didn't you share you started out in oil or gas or something, right? It was a long route to get into ice, as I recall.
Yes, that's correct. This is my second career.
So it's always fascinating for students to feel that they don't have to know where they're going before they get there. There's a lot of discovery along the way. And then I'm skipping through. There is a public tab on my website that has all kinds of reliable information sources, including links to Richard Alley's 2-mile time machine and some of the public documents that have been put together in the U.S. But I do hope that you take a minute to look at some of the videos that we've put together that really give a moving picture of some of the processes that Joe described tonight. There is one on how ice core drills work, so kids really can understand the technology of which parts move where to bring that core up. He mentioned, the longitudinal cut that he has to get for his particular kind of research. So in this ice core processing movie, you can have your students take a look at what happens at each station during the processing of an ice core and which pieces actually go out to be studied for CO2 and so forth. And then the last one is a new movie on the interactions between scientists and engineers who wanted to go back into the West Antarctic ice sheet and get more core at a unique depth where they needed more information. And this is about those interactions and processes that led to a new technology called replicate coring. In the US, we're talking a lot about getting engineering awareness into our science classes and having students distinguish or tell apart what a scientist does versus what an engineer does. So there's a lesson that goes along with this as well called Drilling Back Through Time. Definitely want to take time to thank Joe. Joe, you've been awesome. It's been a real pleasure to work with you, and we thank you so much for taking time out of a special time in London with your wife. Also to thank Polar Educators International for allowing Joe and me this opportunity to share our science and ideas, and of course NSF, who helps to make our program possible. And I would like to just note quickly, for those of you who are doing a lot of climate science study and so forth, we do have another webinar coming up on December 10th, a US-based webinar on Spice Core, which is our ice drilling program's latest large project that's about to kick off next month. I want to make sure you understand this is not a master class. This is not sponsored by PEI, but I do think it's a resource that I hope you'll look into. TJ Fudge is a scientist who'll be talking about what we're going to the South Pole for and what our science goals are. And with that, I'd like to take any questions from anyone that would like to ask.
Well, I would like to say thanks to both Linda and Joe. And what we have done is collected your questions into a document, because I know we are a little bit over our hour and a half time that we set aside for the webinar. And what we will do is pose those questions to Linda and Joe on the discussion group and get all of those questions asked. We've got some great ones there, and looking forward to hearing the answers to those. I'm going to switch back to my screen because there's a couple of things I want to just remind you of before we say goodbye. And Linda, are you seeing my screen now?
Yes.
Okay. Excuse me. Just want to remind you that the resources, the activities that Linda talked about and demonstrated today will be available tomorrow on the website. That's the Polar Detectives activity that she demonstrated. And then also Invent a Word is one that I've used quite a bit with teachers and students, and that will be up on the website too, because I think it helps build that vocabulary. We'll also have a link on the website for you back to the first master class that Linda had talked about with the analogies, and we'll have the link to this webinar if you want to go back to that, but also people that weren't able to make it tonight. Several of you asked if the slides could be made available, and I'll talk to Linda and Joe about that, and if it's okay with them, we will make those available to you. And just a couple of quick reminders about the class. If you haven't joined the discussion yet, you need to first join PEI at polareducator.org and then log into the members area and join the class. If you have any difficulties with that, you can get the technology help from polareducators2@gmail.com. The discussion forum will begin tomorrow officially and run from 30th of October to 14th of November. And to earn the PEI Certificate of Participation, which lists the hours, the professional group development hours for this webinar and the discussion group, join the PEI discussion group. You need to sign into the discussion group and do the pre-survey right away if you haven't already done it. We'd like for you to do that tonight if you could. And then sign in and post responses this coming week and the following week. There'll be 2 discussion threads each of those weeks. And then complete the post survey by November 16th. And then you'll receive the certificate. Future master classes are being planned for spring of 2015. We hope that that'll be available in New Zealand time zone. And then fall of 2015 in Portugal time zone is the plan right now. And just last but not least, again, like to thank Joe and Linda so much for their time. And for any of you that have ever been involved in one of these webinars, you know they don't happen tonight. This has been being planned for a couple of months, and Joe and Linda have spent a great deal of time planning and working together to get ready for this and practicing with the webinar system. And lastly, like I said, it doesn't happen with just a couple of people putting it together. There's a great bunch of people working for you through PEI. All of these people with the website working group and the masterclass working group and our executive committee. And thank you so much to all of those. And to all, a good night. Thank you so much for being here today.
Good night, everyone.